So now we have Jeffrey just met to give us a talk about Optiplanner. So Optiplanner is this amazing new technology that really has just come to light, come to the fore in the last year or so. For optimizing, we call it the business resource planner in the Red Hat product. It's a terrific system that it uses the underlying rules engine, the Drools rules engine, to solve very complex planning problems. And Jeffrey's going to tell us a lot more about that. Jeffrey is the founder and lead of the Optiplanner project, and he's been working in this space for many years. I think 10 more years, something like that.
11 years.
All right.
11 years now.
Okay. All right. So thank you, Jeffrey. Take it away.
Thanks. So so about 11 years ago, I started a little hobby project to solve planning problems. And nowadays, I think it's fair to say it's the most popular open source constraint solver on the planet, basically, in Java, definitely. So let's take a look, right? Optiplanner is a form of a constraint solver. And a constraint solver falls into the area of artificial intelligence. So with the AI hype these days, and a lot of businesses thinking about using AI to basically have an advantage over the competition, this falls into at least partially in that category too, right? Let's get started. So let's start with the traveling salesman problem and the vehicle routing problem. Let me tell you a story, the story of the ultimate American road trip. You might have seen this in the newspaper. It originally started with the Washington Post. They published an article where they said they found the ultimate American road trip. And there was a data genius, a guy named Olson, who had found a way to do this route. So let me show you what the problem was. So there is a road trip for 50 landmarks, monuments, and so forth. And the idea is you want to visit, for example, Mount Rushmore, and you want to visit Liberty Bell, and you want to visit the Grand Canyon. And the idea is find the shortest route, or actually the quickest route to visit all of these locations. And this is what you would get with a traditional algorithm. This is a traditional greedy algorithm. This is the solution you would get. So you would start out, for example, here, and you would drive to Florida, to Georgia, and then back and so forth. The question is this the optimal route? Now, if you want to do it that way, it would take you 271 hours. Does anybody here think this is the optimal route? Or can anybody prove that it's not the optimal route? It's quite easy, actually, to prove that it's not the optimal route. If you look over here, right there, you can see that two paths are crossing each other. You can easily say, okay, if I just instead of crossing them, I just do it like that. I entangle them. You will actually have a shorter route. So that's actually a nice way to see if it's optimal or if it's not optimal, to prove it's not optimal. But so this is the solution that the guy from the newspaper article found. It's much shorter, as you can see. It's 232 hours. And he used a genetic algorithm for that. I won't go too deep into the algorithm here. And this is his solution. And he claimed it was optimal. Well, he doesn't claim it was optimal, but the newspaper article, the New York Times, the Washington Post, and so forth, they all claim that this trip is the optimal route, is the ultimate American road trip. And so the question again, is this optimal? Is this the shortest route you can take? So it's 38 hours better than the traditional algorithm, so it's a good solution, but in fact it's not optimal. So let's take a look here. So in total he has 232 hours, and he's around Iowa. He's going into this direction. But if instead you actually do these trips in that order, so you do a lot of things in quite a different order around Iowa, you actually save 1 hour and 35 minutes. And of course I found this with Optiplanner. Optiplanner, I let it calculate on this problem and actually found this solution there. So that's a way to save an extra hour and 35 minutes on the entire trip. The other problem that was with the original trip is that he presumed that roads are symmetric, what basically means that if you drive from A to B, it's the same time and distance than if you drive from B to A. In reality, that's very different, of course. Here we're driving from B to A, as you can see, and that's a good way to drive. If you would drive the same way from A to B, I think the cops would stop you because you're driving in the wrong way on the highway. So we don't want to be doing that, right? So if we drive from A to B, right, we are actually driving a much longer road, as you can see, as you can clearly easily see, right? So we need to take that into account, that roads are asymmetric. And if we actually take the data from Google Maps and we put that into the system, the asymmetric roads, and we actually do the calculation. So first we take the symmetric calculation with the original data sets, and then we then of course the result is calculated on the asymmetric data set on the real roads as your GPS would send you, right? And then we actually do another calculation where we actually use the asymmetric data in the optimization already. So where we use the correct numbers, where you don't make rounding errors in the optimization algorithm. You'll see that we get a different route around North Carolina. So we're no longer doing it first West Virginia and then to the coast, or first going, well, not first to the coast and then to West Virginia, but the other way around. And the other nice thing about this is we're getting a direction to drive. We're driving from up to down. And that's not really a big surprise. Anybody got an idea why the arrow, the way that we're driving over this route, the shortest distance, will be from up to down and not from up to, and not the other way around here? And the reason is quite simple. If you look at the entire map of the United States, driving clockwise is always better than driving anti-clockwise. Why? Because if you drive clockwise, you turn right on intersections. If you drive anti-clockwise, you turn more lefts at intersections. And it's always bad to turn left at intersections, especially here in New York, I've seen.
What happens below the equator?
Yeah, things might change there. And especially also in England, things change because they drive on the other side of the road. You have to take that into account too. So if you have any questions, feel free to interrupt me, right? So this is Olsen's strip. It's not optimal, as I've shown a minute ago. So this is Optoplanner's strip. It's 2 hours and 25 minutes faster. So it's 1% faster, 15% in total faster than the original traditional algorithm. And it's 21 miles shorter. So by taking a better constraint solver, a better algorithm, we can save a lot of time and we can save a lot of distance. Of course, this is on 230 hours. This might not look much, and this is indeed not that much. But this is an academic problem. This is a traveling salesman problem, right? So why do they call this a traveling salesman problem? It's a long-standing problem where the traveling salesman problem is go visit a number of locations as a salesman and turn back and go back to your home location. So it's basically the same problem. It's just not going to monuments but to customers, right? So now the interesting thing is, if you want to solve a traveling salesman problem, that the MapReduce algorithm, which is one of those algorithms that's really great for querying things on the cloud and so forth, if you try to apply that on these kinds of problems, it doesn't really work that well. Let me show you why. So here we have a number of locations that we want to visit, right, on a map. And we want to find the shortest route to visit all of these locations. So what happens if we say, okay, this is too big, let's just do divide and conquer, right? Or MapReduce, let's just split that up. So we hack it into 4 pieces, right? So we have 4 separate pieces. And for each of these 4 separate pieces, we find some sort of algorithm to solve this optimally. So we get these 4 solutions. So let's forget for a minute how we find those sub-problems, because maybe we do brute force, but even for this little amount of locations, that can already be a problem. And then we take these optimal pieces, we paste them back together, and we merge them back together further till we get a new solution. So this is the final solution where we just so we took these 4 optimal pieces and we put them back together. Now, is the new solution there, is that optimal? And the answer is no, it's actually not optimal. So it is actually, as you can see, 30 points, distance of 30 less above optimal. So taking a big problem, splitting it up in small pieces and solving these pieces individually and then putting them back together does not give you the best way of doing things, right? And so again, that means you'll be wasting resources, you'll be wasting money, you'll be wasting things, right? Now the thing is, of course, that the traveling salesman problem is an academic problem, right? The real problem is the vehicle routing problem. So let me explain you what the vehicle routing problem is. The vehicle routing problem is where we have in the middle of a country or a region or a state, we have a depot, as you can see, and we have a number of delivery locations. So for example, these dots are all delivery locations. So for example, let's say we have a chain of stores. Let's say we are maybe something like Starbucks, which you saw out here, or any store which you see here when you're driving in New York, and you see a lot of stores here, right? They have a lot of. You have to restock those stores. So you might. So you want to send a truck, and you want to deliver, for example, the croissants every morning to Starbucks, right? So a ton of croissants here, 2 tons there, and so forth. And you have a number of limitations when you want to do this. So what are the constraints for this problem? Well, you have a capacity thing. So for example, each truck can carry 20 ton, or I guess here in the States, 20,000 pounds or something like that. And then everywhere you drop a number of weight units of course, you drop a number of weight, and you want to make sure that in total the truck is not carrying more than 20 tons, right? You might also have an expensive delivery over here, which means you need an extra armored vehicle over there. So you can see that this vehicle has more wheels, it has potentially a second security guard sitting in there. So, and that's because one of the deliveries that he's doing is an expensive delivery, so it needs to be another vehicle. You might also have time windows. So you want to make sure that your goods are in the store before 10 a.m., but you don't want to be there before 8 a.m. because then there's nobody there to open the door, right? Or to unload the vehicle. And of course, your biggest thing, well, not the biggest thing you worry about, but all these red ones are what I call hard constraints. You need to fulfill those. If you're not doing those, you have a problem. If you're putting too much things into one vehicle, the vehicle will not be able to leave, right? It will not be able to drive. However, the orange one are the soft constraints, and an interesting one is, for example, the driver wage. Every minute that your driver is driving around, you have to pay him, every hour, of course. And on top of that, you also have to pay the fuel consumption and things like that, right? So if we can actually minimize the amount of time that we're driving, we can actually minimize our expenses, which is very good for our profit margins, of course, right? So, so where do we see this? We see this in any kinds of retail stores, right? Any kind of supermarkets, any kind of store you see around the road which has more than one site where they're selling things. We see this in freight transportation, right? We see this also in person transportation, buses, taxis, airlines, picking up shuttles from people to go through from the hotel to the airport and things like that. And of course also technicians on the road, right? The cable guy who comes to install cable with you at your home between 8 and 10 a.m. Typical time window constraint, typical vehicle routing problem. So how much do you think we can win on this by using better algorithms, by using better things? Well, we did a number of benchmarks, and I did it on the Belgium data sets, which were based on real world, so data from OpenStreetMaps. And I've also done a number of, I've also taken the academic data sets, but the academic data sets that were generated while this one actually uses real world data. And we saw that compared to the traditional algorithms, we could do 50% better on average. So that means for some data sets we only had 9% less driving time. For others, we had 18% less driving time. On average, over those data sets, we come up to 15%. And this is something what I see often. I've heard cases from in production where they said, okay, we can actually cut down our driving time by 30%. But in that particular case, they spend at every site that they visit 45 minutes. So it turns out they had a 10% gain over the every day. So that means 10% less expenses for their drivers that they had, which is that they still have, right? So if you implement this, of course, the interesting thing is to take some historical data, take your new result with Optoplanner, compare them, and see if indeed if it's faster or not, right? Okay. Let me give you a quick demo on that, of course. Here we go. So this is a thing solved with Optoplanner. This is one of the examples. It's one of the web examples. And this is where we've solved it. And you can see here. So let me just. So yeah, this is just. You can see, for example, the green vehicle on the top right here. My mouse is a little bit delayed, so it's a bit hard. I'll stop using the mouse. You can see the green vehicle leaving, going to that location in the north of it's Belgium in this particular case. So it's one of those Belgium data sets and so forth. And of course, we scale out. So we try this with data sets with 100 units. We try it with 1,000 units. We try it with 10,000 locations, right? Scaling out is, once you scale above 1,000 locations, we have a number of tricks in Optoplanner to actually improve that. We have a number of advanced features, something called nearby selection, where it actually takes into account that you probably want to go from here to there. Not always, but at least we want to heighten the probability of testing those things. So we have a number of features to deal with scalability in there. And you can even do, in 7, you can even do partition search, where you do split it up. And you've just heard me 4 slides ago telling you don't want to split things up. That's true. You don't want to split things up if you have 1,000 locations. If you have 10,000 locations, you do want to look at splitting things up. So there's this limit where it becomes interesting to look at that. And even then, you can split things up, solve things separately, put everything back together, and then solve the whole general thing again to actually blur those lines again. Now I'm talking really advanced things when you really want to scale out. So if you want to talk about that, I'm happy to talk about that, but we can do that offline. Okay, let me get back to my slides. So that's a vehicle routing problem. So is this a form of artificial intelligence? Yes, it is, but let me explain a little bit, right? So just to put this in context, there's a lot of hype around the AI now, but AI is a very big spectrum. There's a lot of technologies that fall or partially fall into this category, right? So for example, we're used to this thing, but if a full text search, like you type in the word cat in something like Google, and it gives you a number of documents, for example, about cats, right? This is one use case, right? And another use case might be image recognition. This is a picture, and you want to figure out what is this a picture of. An AI algorithm can give you the output. This is a dog, right? And then, of course, then we have the vehicle routing problem where I just spoke about. We solve this problem, and we can do this with 15% less driving time. Now, the interesting thing to know when you hear people talk about AI is that a lot of people just throw everything on one big pile, and they say, for example, neural nets will solve everything. They won't. Neural nets are great at the middle problem, image recognition. Right? They're terrible at full text search, and they're terrible at vehicle routing problem. Vice versa, Optoplanner is great on the last one, terrible on the first 2. So just to put things in context, you need to use the right AI algorithm for the job, right? So the first case, the algorithm you want to be using is vector space model. So for full text search, for image recognition, neural nets, of course, and for vehicle routing problem, of course, a constraint solver such as Optoplanner. Now, each of these algorithms does have a lot of other use cases. Not just that you can use full text search only for things like, vector space model for things like finding documents about cats, right? You can do recommendations, similarities. You want to look into in that particular algorithm. If you're doing things like voice recognition, machine translation, then you want to look at neural nets, right? If you want to win against the Go the best Go players in the world, you want to combine neural nets with the Minimax algorithm. It was not just neural nets that won that, for the record, right? So sometimes you need to do hybrids, actually. And of course, if you have things like employee rostering, job scheduling, and many of the other problems I'll talk about, then you want to look at a constraint solver such as OptaPlanner, right? And it's not just this, right? So if you want to do pathfinding, which is the shortest route between two locations, like on Google Maps, like when you do navigation driving, it's a search. If you want to do production rule systems, it's the rules freak algorithm in rules, of course, right? K-means for cluster analysis, and so forth and so forth. So beware about people talking about AI as if it's this one kind of algorithm or one thing that will solve everything. The right technique for the right tool. Yeah, okay. So what is a planning problem, right? A planning problem is, so what are the kind of problems that constraint solvers such as OptaPlanner can solve, right? Well, we want to optimize goals and with limited resources on the constraints. And these goals are things like we want to maximize our profit. We might want to minimize our ecological footprint. That's good for our company's reputation, or especially for a government agency, we for good reasons we care about that, right? We might want to maximize the happiness of our employees or our customers for employee retention or customer retention. So we want to take all these things into account. You might value one thing more importantly than the other. That's all possible. We can weight that. You might disable some things there. That's also possible, of course. We want to do this under limited resources, right? So we have employees, we have a number of assets like machines, buildings, rooms, vehicles, those kind of things, and of course time and so forth, and budget. And the big problem here are the constraints, right? Employees don't work 24/7. They need to sleep. There are labor regulations you need to keep into mind and take into account. When you're talking about vehicles, when you have a vehicle and you move this vehicle from New York to New Jersey, it doesn't teleport to Philadelphia, right? So you need to, where you move your vehicles or your trains or your airplanes to, they're staying there until you move them back, right? So those are those constraints which make things hard. So what kind of problems do we see? There's a lot of planning problems, and it's hard to sometimes see how they are the same, and it's hard also to see that which one of these are, so all of these are for OptaPlanner, for constraint solvers. But image recognition is not in there, voice recognition is not in there, so there's a whole bunch of other types of problems which are for neural nets, right? So it's important to see that distinction, right? I'll just pick out a few of these which are interesting. TV advertisements. To decide which TV advertisements you're showing just before the news starts, right? Or or after the kids' TV show. We actually have a case where they use OptaPlanner for that. Right? So they decide if it's if it's at 4 o'clock, we want to show more toy advertisements. If it's at 7 o'clock, we want to maybe show more beer advertisements, whatever, right? It depends on the case, of course. And then schools basically deciding which lecture is in which room at which time. That's a typical classic planning problem. And so forth, right? Okay. So let me, and of course, yeah. So OptaPlanner is our implementation of that, yeah, we have many tests like stress tests, unit tests, integration tests, and so forth. We have our QA department doing additional performance tests and certifications and so forth. Okay. Let's look at another use case. So I've talked about the vehicle routing problem. Now I'd like to focus on the employee shift rostering problem. So what is the employee shift rostering problem? We have a number of employees. And I'll go through some of the code of this, but I'll also show a demo first. So we have a number of employees, 4 employees in this case. You can see 2 nurses, an engineer, and a designer. And we have a number of shifts. So the green ones are the early shifts. The blue ones are the late shifts, so from 2 to 10 a.m. PM, sorry. And the night, those are of course the night shift, the ones with the moons, of course, right? Because then we see the moon. So what are the constraints? There's a bunch of constraints. Labor laws tend to be difficult. Depends on which country you are, but or maybe which state you are. But they can be quite complex. So first thing is only one shift per day. That's relatively simple, right? So you cannot ask a nurse to do 2 shifts on the same day. You cannot definitely not ask her to do 2 shifts at the same time. That's kind of with the laws of the universe that kind of make that impossible to be in 2 places at the same time. You have skill requirements. Like, for example, this shift needs a nurse. So you cannot have an engineer do that, right? You have, like we saw earlier with Chris's example, where he showed that certain tasks, which is also an optoplanner problem, by the way, the task assignment problem, you needed to speak French, so you needed a person who spoke French. That of two is another kind of skill requirement, right? And then, of course, we have things like if you work 5 days in a row, you need a weekend rest of at least 48 hours, and so no more than 5 consecutive shifts. Certain contracts don't have weekend work, other contracts do. So depending on the contract of the employee, we have different constraints. A nice one is forward rotation, if you're familiar with that. That basically says that if you have a morning shift, you can do a late shift the next day. But if you end with a late shift, you cannot do a morning shift the next day because you only have 8 hours to go home, get some sleep, come back. So you won't have enough sleep in between, right? And then the big one here, and I will show them thing, is the day off request here. So that is the biggest problem because a lot of these employees say, I don't want to work Saturday because I want to go out, or I don't want to work Wednesday afternoon because I want to watch my grandchildren, right? So they have all of these day off requests that are in the system, and we'd like to fulfill these, at least if we're, in this case, if you want to care about employee retention, right? And employee happiness. So where do we see this? A lot of it governments, hospitals, courts of justice, but also in call centers and things like that, right? What do we see is when we use the data sets from the academic world I've used here on this benchmark, they come from real hospitals, I've been told, and what we see is 53% more times we can say to a nurse, yes, you get the day off that you requested, right? So we don't magically be able to fulfill all of the day off requests, but we can say more than half the times yes more, which is nice, right? And you can see there's a big difference there with based on. So we had 26 data sets there. They're not that big. They only go up to 750 assignments in that particular benchmark, in that particular data set. But I've worked with much bigger data sets, of course, too, right? Just not something I can publish. So let me show you a demo of that. So let me show you what constraint solving is with our application. So this is, I'm just going to show you. So this is in a browser, right? And this is the OptaShift employee rostering implementation, which is if you're implementing something in OptaPlanner, it's a nice way to see a reference architecture of how it could work. This is a backend on Java EE on Wildfly. You can run this on OpenShift. And there's a REST API. I'll show that later, but there's a REST API over there. And the UI, this UI is implemented in Grid, but you can easily throw out the UI and implement your Angular UI or something like that, of course. But we prefer to go with Grid, of course, right? So what do we have here? We have a number of skills, electrical and mechanical, and we can add skills, all right? We have a number of spots. So what is a spot? We're actually doing employee rostering for an assembly line in a factory. Right? So think about a steel factory, a car factory, something like this. In this particular case, it's a car factory. Now, to build a car, to build the assembly line of a car, we need to put the battery in the car. We need to put the bumper, the doors, the engine, and things like that. We need to put all those things into the car, right? So, and each of these spots has a skill. So, for example, to be able to put in the battery, you need to have the electrical skill, of course, right? Okay. Then we have a number of employees who work for us. In this case, about 40 employees, and you can see each of the employees has one or more skills, right? So, for example, the third one, Amy Green, has the electrical skill. She would be a good person to do, for example, to fit that battery. And then we have the spot roster. So based on all of these locations where we need somebody to work, well, now we know on Wednesday morning we need one person in each of these locations. On Wednesday afternoon we also need one person in each of these locations. And Wednesday night, one person, and so forth. You can see the radiator, we don't need to put radiators at Wednesday night, apparently. This is a generated data set, so it might not always be perfect here. As you can see, I can add places. I can, for example, say, Wednesday night, I need 2 persons to put the battery, because they need to be, one person might not be awake and it's a dangerous job. And of course, if you do it on Wednesday night, we need to do it at Thursday night too, right? And we can also remove things like, for example, we don't need doors during night, so I'll remove that, right? Okay. Okay. So based on this, let's fill this in. Let's solve this. So here's the big green button, the magic button where we say Optoplanner, solve this problem for us. You figure it out. It's too hard, or we want to get a better solution. So as you can see, Optoplanner is solving it now, and he decided, for example, that right now he's thinking to use Chad Green to do the battery on Wednesday morning. And he still changes. He's still finding better and better solutions as you give him some more time. So actually, he found a feasible solution in 1 or 2 seconds already, but it then took him to get a better and better solution where we fulfill some of the soft constraints, which I'll explain in a minute. If you give him some more time, he finds better and better solution. Of course, depends on if you put hardware in that, you can actually get everything a little bit faster too, right? Although throwing hardware at the problem is usually not the way to solve these kinds of problems. These things, if you have scaling issues with optimization problems, throwing hardware at them is a drop in the ocean. It's not a way to solve it. You can buy a computer that's 10 times as fast. If you have a scaling issue, it will not make your problem go away. Okay, that being said, so let's take a look here. So the battery is Chad Jones, right? And of course, if you look into the employees and we look at Chad Jones, he has both skills, so of course he has the electrical skill, right? And if we now look at the employee roster, we can see that Chad Jones over here is indeed doing the battery on Wednesday morning, and he's doing the bumper on Thursday morning, and he's doing the doors on Friday morning, right? Now we can easily see a number of things. First of all, no person has two shifts on the same day. That's good. Second thing is that between any 2 shifts of a person, there is at least 10 hours of sleeping time, let's call it like that, right, or rest. Because all the shifts are 8 hours, that actually means that there's at least 16 hours between any 2 shifts. So you can see that here. He's working until 2 a.m., 2 shifts, next shift, 2 shift, next shift. So sometimes it's more. Let me see if I can find a case here where it's more. Yeah, so this one over here, this one over here, you can see 3 empty shifts, and then a shift that he's working. But you will never see a case where you see 2 shifts for 1 person that are next to each other or only one in between. So that's one of the hard constraints we're taking into account, along with the other hard constraints of the skill which explained earlier. But you can also see soft constraints happening. So what are the soft constraints? That's those traffic lights, right? So red means I cannot work, right? And you can see nobody has, so for example, Dan King over here, he is red for Wednesday afternoon. He cannot work. Maybe he took a day off. Maybe he's undergoing surgery. We don't know, but we know he cannot be there. So that's red, right? So you can see Optoplanner does not schedule Dan King to do anything on Wednesday afternoon. He also said he doesn't want to work on Wednesday night and Thursday night. Maybe he's still recovering from whatever he did on Wednesday afternoon, so he doesn't want to work, but if he needs to, if he's forced to work, he will come. So that's a soft constraint, actually. And you can see that Optoplanner, in this case, there was enough room in the data set to also fulfill those things, to not assign them in that case. On the other hand, they can also ask, I'd like to work. For example, Chad Jones wants to work on Wednesday morning. You can see that we are able to give him that, right? So sometimes we are able to do that, and sometimes we are not. Like, for example, here, Beth Green wants to work Wednesday afternoon, but she's not actually getting a shift at that point in time. And why is that? Well, that's because of all of those other constraints, all of those other employees, all of those other shifts that are being assigned. We can probably fulfill that We can maybe give her the Windows one, but where do we do the sunroof then? If we then would do the sunroof to Beth Jones, we would violate the hard constraints. So it's actually better this way, right? So it's like this big jigsaw puzzle, right? You pull on, or this big spaghetti, you pull on one thing and something else breaks. It's very hard, once you have a good solution, to improve it further. And that's why a lot of people think if they see a good solution, this is the optimal solution. We are doing the best thing we can do for a company. And they're not, of course. They can do 15% in some cases, like in the vehicle routing case. Better, depends on which case you're talking about and how well you're already doing. But it's not because you don't see the better solution that it's not there. That's why using these algorithms, you can actually just run them and see if you run them longer with different algorithms, and you see if you find any better solutions, and then you know that you're not doing the best you can in the time you're currently solving. Okay. One interesting thing about all this is, what I can do right now is show what happens if I say, okay, Chad cannot work the battery morning, right? He falls sick, right? Let's say he falls sick most of that time. He's now a long time where he is not able to work. This is bad. Let's solve this again. And you'll see one of the first things that OptoPlanner will do is he will actually move Chad Jones away of doing any work at that point in time, which makes sense, of course. And you can see this trickles down to the others. We can put something in OptoPlanner that the way this affects the rest of the existing schedule, we can actually make this as little as possible. That's not implemented here, but if you would do this on the day itself, you don't want the entire schedule to change. It's very disruptive. If you want to don't want to have disruption, we can actually put something in OptoPlanner that we can add a constraint where we say, fix this because Chad cannot show up. Fix that hard constraint which is broken, but also do that with as minimum disruption. So leave as many of the shifts on their old position, and that's pretty easy to do. Okay. One more thing I want to show you here is that the user is still in control. So what I'm going to do is I'm going to add some things here. But here on the battery, what I'm going to do is I'm going to edit this one, and I'm going to currently it's assigned to Dan King, and I'm going to assign that to Amy Cole, for example. And you can see it is locked. Do you see? So I've added two shifts that are assigned to be scheduled, and I've said that Amy Cole will do the battery, and originally it was Dan Cole according to the plan that OptoPlanner found, and this is locked. That's forced, right? So that basically means that says I know that you want to assign Dan King, right, OptoPlanner, but I'm the boss, right? And this you have to listen to me. For whatever reason, maybe it's political, maybe it's just because whatever reason, I'm assigning Amy Cole to that shift right now, right? So, and then we do solve this, and you will see that OptoPlanner will start moving things around, will assign those two shifts that are not that new shifts that I created. But whatever he does not touch this thing. Amy Cole will always be assigned to the battery. And I can do this to multiple shifts, right? I can say, I can override 3 or 4 shifts, and OptoPlanner will plan the rest. So I do half of the plan, and the other half, the difficult parts, still with the things I already did, taking those into account, OptoPlanner has to figure it out. Good luck, right? And that works really well. So it's not an all or nothing thing. It's not we do automation and we throw manual intervention overboard. No, we have manual intervention is still possible and it's still useful in particular cases. Maybe, there's always edge cases that you might not have implemented in constraints yet, that you might want to override the system for one or multiple shifts, and that's quite useful. Okay. So how do you implement this, right? So now I'm going to go a little bit more technical. So if you implement this in Java, so we have, of course, the workbench, the thing that Alex spoke about. We have support for OptoPlanner in there. But now I'm going to go, how do you do it without the workbench? How do you do it on the engine level, right? On the lower level. So what we do is we need to do 2 things. We need to define the domain. So we have an employee, we have a shift, and an employee might be in a constraint, so it might be a big domain hierarchy, but I've just shown the 2 most important classes here. And you have a score function, right? So you have your hard constraints, at most 1 shift per day, skill requirements, and your soft constraints, at least day off requests and so forth. Actually, at least 10 hours between shifts, that's a hard constraint in the implementation I showed earlier. Depends on which company you're solving this for, right? Based on that, we built something called a solver factory. We have 1 instance of this per application usually. And then every time we have a data set, we first build a solver. And then we have that data set as input. So here we have a data set with 3 employees with a number of shifts, 8 shifts. And we need to assign those. And you can see that 2 employees also have filled in a day off request, right? So this goes into the solver. OptiPlanner starts solving, thinking, thinking, not really thinking. It's an algorithm that just goes to a lot of combinations and weighs those two in a smart way. It's nowhere it's not a danger for mankind or anything like that. But anyway, and it brings up a solution, right? So you can see here all the shifts are assigned. It does break one of the day off requests, which makes sense because we have two shifts on Wednesday and we have only 1 employee that wants to work. So it makes sense that one of the soft constraints will be broken there. Okay. Okay. So how does this work in Java? How do you do this in Java? Well, you have your domain class. So you define the roster class, the shift class, the employee class. This is all. So you can add any type of class you want, and OptiPlanner can take those into account. You work with plain old Java objects. If you've seen any of the other constraint solvers, they are usually based on int arrays, double arrays, things like that. Decimal points and so forth. They're not working with shifts or employees in many cases. And so this is a much bigger advantage because you can actually reuse your Java code. You can plug in Java methods and so forth. So next thing we do is based on a solver configuration, we build a solver. And then, this is the most important bit, of course, solver.solve my problem, and I get a solution. And that method will go away, will take some time, depending on how you can configure it in multiple ways. You can say, okay, I wanted to give it a minute or I want to give it 10 seconds. But you can also say, just solve until you don't find a better solution anymore, or solve until I stop you from another thread. There's many, many different ways of configuring that. But so at some point it returns, and you can even listen as it finds better and better solutions, so you don't have to wait until it returns. And then here I just do a system out, right, where I show the employee to each one, right? Okay. Yeah.
The problem and the solution both share the same class.
Yeah. So the problem and the solution both share the same class. Might seem a bit weird, but interestingly enough, you can take your solution, and that is actually can be the problem again. Yeah, because you add one empty shift, but your other 99 shifts are already assigned, and you want to have OptiPlanner start from those 99 shifts already assigned. You don't want to start from scratch again. So that's why this is the same class. So you can, and this is something very interesting when you do something that I haven't shown today, which you don't have the time for. It's called real-time planning. In real-time planning, we have a warm solution that's running, that's solving, and the problem changes, and in 12 milliseconds we can process that change and get back to a feasible solution. So in milliseconds. And it's something you cannot do if you do cold starts. It takes at least seconds to get to a feasible solution. So that's quite powerful. Okay, so we need to define the constraint, the domain. So you can see that the domain in this particular case is actually more complex. So a shift is assigned to a spot, a shift belongs to a spot. A spot belongs to a skill. A spot has a required skill. There's a relationship between skill and employees, so an employee has multiple skills. There's a time slot that a shift belongs to, and so forth. And that's here, and this is the big thing here. A shift needs to be assigned to an employee. And that starts out as NULL, and OptiPlanner will actually fill that in, right? So this is important if you're actually implementing this. This is the thing that OptiPlanner needs to, OptiPlanner takes everything into account for the constraints, but this is the thing that OptiPlanner changes, this relationship. He will take the current employee, which usually starts out as NULL, and assign it to, for example, like we've seen before, Dan King or something like that. And he might change it as he's trying out newer and newer solutions. So he has like 100 shifts, maybe 20 employees to choose from, and he's trying newer and newer solutions. He's trying one of the other employees, right? Or 100,000 shifts and 20,000 employees, of course, it kind of depends, right? Okay. Implementation-wise, if you look at these classes, these are just plain old Java classes, right? A class spot with a name and a required skill, an employee with a list with a name and a list of skills, and you can see here we have some Java code, and we can reuse that later in the constraints and so forth, right? Okay. And then the shifting is where we had that special thing. So there, what we have there is we have the employee, which is a planning variable. So that's the thing that changes during solve, right? So OptiPlanner needs to know about that, so you need to annotate that with @planning variable annotation. It's kind of like Hibernate for the people who are familiar with that, like JPA actually. You just specify where OptiPlanner can do changes, right? Back to something more business for the business people also. How do you decide which solution is better? And that's based on something called hard and soft constraints. So here we have a problem: 3 employees, 6 shifts, 2 day off requests. Let's suppose we deliver this solution. So in this solution, we get all these shifts assigned, but we have one shift where somebody needs an engineer and we're not giving them an engineer, and we have one, the same case where we have 2 shifts on the same day for one person. So that's bad, right? So that breaks hard constraints. So how do we score that? Well, we score that as -2 hard dash 0 soft, right? Okay. Why is this important? Well, let's take a look at another solution. Here's another solution. And you can see now we are not breaking any hard constraints anymore, but we are breaking a number of soft constraints. There's no 10 hours between those two shifts twice. We have this 2 twice, and then there's a day off request that is denied. This one will score as 0 hard, but as -5 soft. Why -5 soft? Well, we lose 2 points here because we have 2 hours too few here. It's 8 hours instead of 10. We lose 2 points here because, again, same reason. And we lose 1 point here because we deny a day off request. Now, of course, as a user, you can configure this that this is a higher weight. You can play with the weights, and you can say day off request is much more important to me than this soft constraint, and you just multiply that weight by a bigger number, right? You can play with that, or your business can play with that. Now, gives us this thing. So, how do we know? How does OptiPlanner know that this is a better solution than that one? You can all see this is a better solution, right? It's not breaking hard constraints. It's not telling nurses to act like engineers or vice versa. So how does OptiPlanner know that? Well, OptiPlanner looks at this score that you have to figure out based on the constraints. You have to give this number, and it says, okay, I look at the hard constraints and I see this one has a higher number. So that's -2 hard. This is 0 hard. Higher number wins. And the reason, by the way, that this is negative is because you can also have positive constraints, right? So you can mix positive and negative constraints. But most of the time, you'll only have negative constraints. You'll only have negative numbers. So OptiPlanner knows, okay, I look at, when he compares 2 scores, he only looks at the hard constraints. The one with the better hard constraints wins. Very simple. Now suppose we have a third solution. And this third solution, we do it like this. And we now see that we only have one soft constraint broken. So if you actually look at the score of this, the score is now no hard constraints broken, 1 soft constraint broken, total 0 hard minus 1 soft. Given these 3 solutions, which one would you prefer? Last one, yes. So, and how does OptiPlanner know that it needs to deliver one? Well, quite simple. It looks at the hard constraints. It says, okay, I can forget about the top one because these 2 have 0 hard constraints broken. And then, only then, it looks at the soft constraints and it says, okay, -1 is better than -5, so I'll go with the bottom one. Right? Does this make sense? Yeah. Okay. So this is important as business people are implementing this to know what a hard or soft constraint is, to know what weight is, and to model their constraints as such, right? Okay, I'm running out of time, so I'll just go a little bit further. So again, so what happens is we give it the domain classes, we give it the score function. We can do this in the Drools language, or we can do this in the Java language. And then we just input the problem, and we get the solution after some time. Okay. So when do we solve? One thing when you cannot just solve every. So one thing we do is called continuous planning. Instead of just solving for a week, we solve for a longer period of 3 weeks. So we make sure that whatever we do here, we don't end up with a situation that brings us in a difficult situation the week after. So we plan for, let's say, 3 weeks. And then if we then the next day or the next minute or the next week, doesn't really matter, we need to plan again. What do is we slide this planning window to the side. This is now history. This is now locked, right? Similar like it was locked in the application. And we take this into account, of course. For example, if you cannot work 5 days in a row, we have to take this into account that this person needs to be free. And we solve that again. And you can see some things change. For example, this late shift has now become a night shift. So there's some swaps there, and that's fine. But this allows us to do continuous planning, right? To not plan something and then independently. We can keep planning. We can plan 6 weeks in advance, and we have cases like that, right? Okay, and we keep rolling that window, of course, right? Okay. And of course, who's in control? The user that I showed earlier, right? Okay. So summary: OptoPlanner solves planning and scheduling problems. Adding constraints is easy and scalable. I haven't gone into that. I didn't have the time, but I'm happy to show that offline. And combining algorithms is also quite easy. I haven't shown that part in detail either, but OptoPlanner implements a whole set of optimization algorithms, and you can easily try each one of these, and you can easily even have a toolkit called OptoPlanner Benchmark to try out these algorithms against each other and see which is the best one. And that's what I've been doing a lot to figure out, which is the one that I would put in default. It's which is the one you get from default. Now you don't have to know those algorithms. It's kind of like the garbage collection in a JVM. If you want to power tweak it, you can do that. If you don't, but 80% of the people shouldn't spend their time doing that, right? It's something you do when you want to get that extra 1%. And if that's 1% of a 9-digit number or a 7-digit number, whatever the case, it might be worth actually spending 2-3 weeks power tweaking that. Okay. If you want to try any of this out, I didn't actually show the normal swing examples, but you can try this out to go to download OptoPlanner. So go to optoplanner.org, just download them, try them out. And if you want to try the Opta Shift example, that's a little bit harder. It's on our GitHub repo. And the web examples is here. So the one with the vehicle routing one is in this directory. That's a WAR file you will find in that directory, in the web examples directory. So if you want to try out these examples yourself on your machine, do try them out. And of course, you can build from source for the people who like to do those things. If there's any questions?
Yeah. So, what you have shown, some of the problems you showed can be expressed as a set of objective functions and linear programming kind of constraints. You can use a classic simplex algorithm
Yeah.
to do the optimization. How is OptoPlanner different?
First of all, it doesn't use the simplex algorithm. It uses meta-heuristics to solve these problems. A combination of constriction heuristics and meta-heuristics, actually. This gives us the ability to scale better. Gives us the ability to reuse Java object classes in the code itself, and gives us the ability to reuse Java methods.
Let's focus on the mathematics.
Yeah.
Worry about the Java, etc. Right? I mean, there are versions of simplex which are polynomial time, so they should scale.
Yeah, if you have a problem which is in polynomial time, you don't want to use OptoPlanner. In that particular case, which is none of the cases I've shown, of course, you don't want to use. You might not even want to use constraint solvers. If it's solvable in polynomial time, you want to just use the.
Polynomial with a high exponent. I mean, n raised to k, where k can be very high, so there could still be a.
Can you give an?
scalability issue there.
Yeah, if you.
Anyway, so let us say okay. So you're telling me that it's for all the some simplex problems can get into NP hard, which is what he said, and that may cause a scalability problem. Your heuristics brings the complexity back to polynomial range. Is that what you're suggesting?
Not to, well. The question is, of course, can you do in polynomial time find the optimal solution, right? These problems are NP complete or NP hard. Right now, 50 years, nobody has found it yet, right? There's a lot of people who claim they have an optimal solution. Nobody has ever done it because otherwise they're the next Alan Turing, right? So they don't, right? It doesn't exist, no. What we do is we find the best possible solution in the available time. Yeah.
So these are not provably optimal, but
no.
they're optimal in a very contextual, given a limited set of resources and time, they're optimal within that context.
Yeah, I use the word best there instead of the use optimal.
Okay, fair enough. Okay.
Yeah, because that's an indeed important distinction.
Whatever you're talking about, heuristics can be expressed as constraint equations in a linear programming approach, potentially. Yeah. Or maybe not, so that's something we can take offline.
Yeah.
So, okay. That's
okay. Any other questions?
I do actually.
Yeah.
I've been to 3 AI events in the last month. This is the 4th. And you were the first to say he with AI.
Ah, okay. Is it she?
Either was they or it.
Okay.
I want to know, as a harbinger, where are we going to as IT professionals? How are we going to refer to AI? AI, he, she, it. Programmers, so we are they, or he or they, or if there's a group of ladies. I mean,
I should probably have said it. I don't think of it as a. At this point in time, we're nowhere near a G AI, right? A general AI, which might be something we don't want to get into in the first place, right? But this is why this is solving particular types of problems with a particular AI algorithm. That's a completely different case where you have something that would be a general AI, which with all you've seen the movies around in those cases, right? Yeah. And then you might want to call it here, but I should have called it I presume.
I just have to go with that. I'm sorry, guys.
No.
See where I'm going, right?
Yeah. Any other questions?
So, I mean, this is incredibly exciting and interesting, especially because I work in a system and there's lots of optimization problems to solve. How does this translate more practical? If I want to edit the rules, if I want to, or do I just get what is out of the box, or I can just build everything from, all this program? I mean, unlike in rules where there is very easy, I mean, there's this workbench, there is,
you can use the workbench.
Yeah.
So we have Optoplanar workbench, which I haven't shown today.
Okay.
You can use Optoplanar workbench, and it actually integrates with the rules workbench. It's actually part of Business Central, and you can. We have a couple of examples: the Opta Cloud example and the an employee rostering. We have actually an employee shift rostering example in there. Now it's still early stages. This is one of the reasons I don't want to show it, because we're still early stages. But we do have, for example, if you write your rules in the guided rule editor in the workbench, then you can now say this impact is a score -1 soft or -1 hard.
Right. I mean, so if you just want to, let's say, take one of your 5 or 10 or
Yeah.
15 examples, and you just want to tweak the scores.
Yeah.
How do you do it today? Do you have to just go in Java?
I'm an engine guy. I want to see it in a text file, right? So I'll go to the DRL file. But
So all these come with DRL files?
yeah, so the examples I've shown now come in the DRL file, but I can show you actually some of the screenshots I have for the other case.
Because these were all Java, right? I mean, the previous releases, I think,
Yeah.
now supporting DRL? Is that recent?
No. We have supported DRL from the beginning. You can choose whether or not to go with DRL or with Java, and it's actually better to go with DRL because you get something called incremental score calculation out of the box. And now you want me to explain? I can explain that, but I'm going to eat in a lot of people's time. I'll do that offline.
I just want to close out that. The good news is the next release is not coming out. There are going to be 2 examples on Mars. Okay, the implied rostering and then the loading.
Actually, 3. That's good.
That's what is pretty promising. I'm not sure to get it out. So exactly what we're asking for. We want to be able to take that.
That's an old screenshot.
So
Yeah.
everybody cannot be like conjoined, right? There are people like me who don't want to do a lot of coding, so I want to just get it done. So it's easiest to go have it.
And that's the next community release, or?
I'm going to just talk about the
Okay.
Yeah. So here you can see that we say we want a solver and it needs to run for 5 minutes. It's maybe not clear at the back, but so we have integration in the workbench there. So we're definitely working on that. So thanks for listening.